All right, thanks, Gil. All right, so, and thank you all for sticking around. I know it's getting late in the day, so I appreciate you guys sticking around and listening to me talk. So we're going to be talking about a couple different topics here related to car hacking. We're going to start off talking about in-vehicle networks, so the types of networks that are running around inside your vehicle. We're then going to review the attack surface, and then we're going to do some analysis on a telematics ECU and hopefully develop a plan that would show how we would attack something like this in the wild. So cars are made up of multiple computers called electronic control units that control everything from your engine, your power steering, your anti-lock brake system. You have those controls in your steering wheel that allow you to, control your hands-free set or increase the volume. That would be your steering column control module. That's an ECU. And then you have more advanced features like, some cars have adaptive cruise control where they can, speed up and slow down based on the car in front of them. They can keep the car in the lane if you start to veer off. Parking assist module is another more advanced feature where the car can kind of help you park. And then telematics, which is what we're going to be talking more about later. The general trend for cars is that the number of ECUs has gone up. So I made that little graph there based on some schematics I had for a couple different vehicles. The bottom one in the red is my car. I drive a 2010 Subaru Outback. We're going to be playing with that more later. When I bought my car in 2010, it had 9 ECUs. Now, if you look at 2016, last year's model, there's 19 ECUs in the car. You look at something like a Lexus or a Lincoln that has a luxury car that has a lot more features. Those cars started with a lot higher numbers, and they've increased as well. So all these ECUs in the vehicle are connected using multiple different protocols. We're going to be talking a lot about CAN because that gets a lot of the security research that has come out has talked about CAN bus, so we'll be talking about that. That's basically the main command and control protocol in your car, but there's other buses as well. There's MOST, so MOST is for audio video content within your car, so if you've got like a touch screen that connects to your radio, that might be going over the MOST protocol. If you've got kind of a disc player that's connecting to an amplifier in the back, that audio content might go over the MOST protocol. There's LIN. LIN is basically a single wire serial bus. It was designed to be cheaper than CAN. So things that are connected with LIN bus, maybe like your seat controls, your seat heater, things like that. There's FlexRay. FlexRay was designed to be faster and more reliable than CAN. So for example, if you've got an ECU in your car, we talked about adaptive cruise control. So if your car basically can detect when the car in front of you stops and apply the brakes automatically, applying the brakes is probably FlexRay because that needs to happen right away and very, very reliably. And then we're starting to see Ethernet in cars as well. So manufacturers are starting to sort of separate out the comms, sort of the modems, the cellular modems, Wi-Fi modems from the ECUs that actually understand what to do with the packets. And you may see Ethernet kind of bridging, sending that data from the modem down to those different ECUs. But the one that gets the most play is CAN, and it is the main command and control bus in the car. The other buses, things that are connected with those usually hang off of a CAN network. And CAN is very simple. It's a 2-wire bus, uses differential signaling, and basically everything on the bus sees every message that's put out there. So if I put a message on the bus, everybody sees it and they can decide what they want to do with it. Finding CAN networks in your car is pretty simple. The resting voltage of the CAN line is 2.5 volts, and then it fluctuates between 1.5 and 3.5. So if you want to go hunting for CAN lines in your car with a multimeter, that's kind of how you would do it. Standard baud rates, lower speed CAN networks operate around 125 kilobits per second and 250 kilobits per second with the upper end of 1 megabit per second. Oops. Oh. So my car, a 2010, has a single CAN bus, but modern cars have multiple. This block diagram I drew based on some schematics for a 2015 vehicle, and you can see it has 3 different buses. It's got iCAN, HSCAN, MSCAN. And you can see certain ECUs are only on one bus or the other. There's a couple that bridge them. So the IPC, the instrument panel cluster, that bridges the iCAN and HSCAN, and then the APIM, which is basically the protocol interface module, that's connected to all of them. The other thing you'll notice is up in the corner there, the DLC, that's the OBD2 or maintenance port. We're going to be talking about more of that later, but you can see that's only connected to one of the buses in this particular vehicle. So the CAN frame is just like the bus, is equally simple. There's an arbitration ID field. It's 11 bits. It can be extended out to be 29 bits based on whether or not the identity extension bit is set. There's a length field, and then the payload can be anywhere from 0 to 64 bits, and that's pretty much it. What the arbitration IDs are and what's in the payload is very proprietary. There's no real standard there with the exception of diagnostics, and even then some of the responses coming back are also vendor specific. So if you want to monitor CAN traffic in your car, all cars after 1996 support onboard diagnostics. The port usually looks like that. It's called the OBD2 port. Most of the cars that I've seen, it's basically underneath the steering column on the left side. And that port is connected right up to the CAN bus. So we use, I use a PCAN adapter. The adapter costs around $300, and then the OBD2 to DB9 cable costs around $10. So you can plug into that, and this is sort of what you'll see. You want to queue up the video? So while he's working on that, so there's a lot of different tools for sniffing CAN out there. Linux actually has socket CAN built in, so there's a free set of tools called CAN utils. And what we're going to be seeing is we're going to be seeing two of them: CAN dump, which is basically TCP dump for CAN, and then CAN player, which basically highlights bytes that change. Nope, other one. So one of the ways that you can kind of try to figure out what's going on in your car is you can kind of monitor the bus, and you can kind of watch what happens as you change, as you take different actions. So for me, pressing, my car has a button that allows me to turn on and off the cruise control, and you can kind of see that. There you go. All right, so we'll see that there. So on the right is CAN dump, the left is CAN player, and you can see my car is doing nothing but idling now, so there's traffic happening all the time. These two arbitration IDs, 231 and 235, those are the ones I identified as being related to the cruise control button. So you see 6200, you see those last bytes change there. 6200 means it's off, 6801 means it's on. And all I'm doing is pressing the button that you can see on the steering wheel to turn it on and off. So that's kind of a real simple way of how you can figure out what's happening on the CAN bus. CAN traffic is, you can think of it more as sort of relaying state of different things in the vehicle. So when we talk about turning the cruise control on and off, it's not like a single packet that says, hey, you're on, hey, you're off. It's kind of a constant stream of messages that are just like, hey, the cruise control's on, it's on, it's on, it's on, it's on, now it's off, 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 off. So it's constantly relaying state about different things in the vehicle. Go back to the slides. Actually, I think the next one is another video, so you can just queue up the next video. So CAN networks, because a CAN network, because there's no built-in source identifier, there's no non-spoofable source identifier, and because everybody on the bus sees every frame and can decide what to do with it, CAN networks are subject to injection attacks. So one of the issues that you run into when you're injecting messages into a CAN bus is that you're injecting messages. In this case, I'm going to show in trying to inject the cruise control message. But you're injecting the messages, but so is the real ECU. So the real ECU that is constantly sending the messages saying, hey, the cruise control's off, 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 and my adapter is sending the message saying, hey, it's on, 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 on. So you're going to kind of see that behavior here, and you're going to see the light flicker. Go ahead, play it. Come on. No? Okay. Try it again. Okay. There it goes. So you can see that light kind of flicker back and forth there. What ends up happening is that, as I said, I'm sending the message, the real ECU is sending the message, and there's confliction there. So how the ECUs handle confliction basically varies depending on what it is. Some dumber ECUs will just basically respond to whoever's transmitting faster. But other ECUs, can detect when there's conflicting information, and they can take various actions. For optional features like sort of parking assist, adaptive cruise control, the safe action to take there would basically be just return control to the driver. But other ECUs may not be able to do that. Like if you're messing with your engine controller, they may just like raise an error code and then keep going. So everything we've talked about so far is a physical attack, so I was physically plugged into the OBD2 port, injecting CAN messages into the vehicle. So how you would actually go about doing this remotely, you would need to kind of exploit one of these other external attack vectors, and then go from there to actually pivot from there to actually being able to send messages on the CAN bus. So there's a lot of different attack vectors in the vehicle. These are a couple that these are the ones that I could think of. So cellular gets a lot of play. Cellular is the interface that, cellular and Wi-Fi were the interfaces that Charlie Miller and Chris Velasek attacked in their 2014 GPAC. They found basically an open port, a port that was open on both of those interfaces that just allowed them to execute code. It exposed an interface that just said execute. V2X is something that's coming. V2X is sort of a short-range wireless protocol that's supposed to allow vehicles to communicate with each other and also with the infrastructure. So one of the use cases is basically like, your car approaches a traffic light and there's an emergency vehicle coming through. Emergency vehicle says, hey, I'm an emergency, sends out the V2X message, and your car stops automatically and lets him pass. Bluetooth, we all have Bluetooth in our cars now for hands-free. TPMS are some wireless sensors in the wheels that wirelessly transmit what the tire pressure is. We've probably all seen the lights come on the dash when the tire pressure is low. And then, cars that support sort of blind spot detection, adaptive cruise control, and even moving into autonomous driving, they have sensors all around, right? There's sensors on the front and the rear, on the sides that kind of detect when there's another vehicle approaching. So inside the car, we have some other attack vectors. We already talked about OBD2 on the data link connector. People found an exposed Ethernet port on Tesla, so there may be some other exposed ports inside the vehicle. Web browsers, people are starting to put web browsers in cars, and I believe this fall of Black Hat, Keen Labs is going to talk about a vulnerability they found in Tesla's web browser. A lot of our cars can parse audio, video files, MP3, M4A, so there may be parsing vulnerabilities there. And then we have our in-vehicle applications as well, and some manufacturers starting to talk about allowing people to go out to app stores and upload their own apps that would run on the car. And of course, USB ports. We use, those of you that have Android Auto or Apple CarPlay, you may connect your phone up to the car using USB. And some vendors also do map updates and also software updates via USB. And of course, we can't forget the two on the bottom. Telematics mobile applications. A lot of people have found issues with those that allow them to do things to other people's cars, unlock, find the car. And then a lot of telematics services connect back through some sort of back-end network. So if an attacker was able to penetrate the enterprise and pivot to the right position, they may actually be able to manipulate the vehicles. So let's take a look at a telematics ECU. So our goal with this analysis, we're going to basically try to develop a plan that's going to allow us to find vulnerabilities in the cellular interface that would allow us to get access to the vehicle's CAN bus. So when looking at an embedded device like this, first thing that we normally do is inspect the hardware, but then try to get a copy of the firmware, and then we're going to do what I'm going to call firmware profiling, which basically means some high-level reverse engineering, just figure out what we're working with, operating systems, communications protocols, and things like that. From there, hopefully, we're going to come up with an attack plan that we could then use to go after a vehicle using this ECU. So this specific ECU has two boards. This is the top board, the main board. It runs an NXP 32-bit PowerPC processor that has two integrated CAN controllers. Integrated CAN controllers, not every ECU has that. Specifically the 2014 Jeep that Charlie Miller and Chris Velasek hacked, it actually had a separate chip, a V850 chip that did the CAN bus interface, and then another ARM processor that handled sort of the main functions of the ECU. So when they got access to the ARM processor, they then had to pivot to the V850 to be able to control the CAN. We wouldn't technically have to do that here because we have integrated CAN controllers. We've got this external flash memory that holds all the firmware for the main processor, and then we've got DRAMs, external DRAMs. We've got 250 megabyte DRAM on the front and the back of the board. There's a bottom card here, sort of a daughter card. This card uses a Qualcomm QSC6055 chip. This ECU is a couple years old, so it's using CDMA1X and CDMA2000, which were the protocols that Verizon used, 3G protocols that Verizon used in the US. It's got NAND flash, which is probably for the QSC chip. And then on the back, there's another DSP specifically for GPS. So this ECU has both cellular and GPS built in. So next step would be to get a copy of the firmware. When dealing with something like this, there's a couple ways that we can do it. There's diagnostic services built into the unified, built into the CAN protocol, but we didn't really have a chance to talk about those. But one of the services that an ECU may support, may or may not support, is request upload. So we may be able to use that if we have a maintenance tool. We may be able to get security access and download firmware that way. If we've got Wi-Fi integrated into an ECU, we may be able to take advantage of Telnet, SSH, FTP servers that are running to get access to the firmware. Besides from that, we have to do some hardware hacking, so look for latent JTAGs, UARTs that are on boards, monitor sort of inter-chip communications. We might be able to recover partial pieces of files there, and then chip desoldering. I'll say for this ECU, we defaulted to chip desoldering because that was kind of the last option that was left. So we desoldered that flash chip, put it into a flash programmer, and read it off, and what we get is sort of a raw flat memory dump. So these memory dumps have structure. After staring at this one a while, figured out what the structure is. So the top, we have the interrupt vector table, the bootloader. We have two IFS images. So I should say this guy's running QNX, which is an RTOS that you commonly see in vehicles. The IFS is the file system partition that holds the main operating system. So we have a primary one, and then we have one for reflashing. And then we have 12 different flash file system partitions. Getting this stuff out, we used a combination of tools that QNX provides and then also tools that we wrote to kind of go in, parse the file system partitions, and then pull the files out. So we're interested in comms. So one of the file system partitions that we pulled off of this thing is mounted at a directory called /PKI assert. So that seems pretty interesting if we're interested in comms. So when you're dealing with files and reverse engineering, a lot of time, those files get opened based on the string name. So if we use this, I use this simple shell script, which basically just runs the strings utility and greps for specific strings through all the files and all the partitions that we extracted. And we see that all three of these certificates, they're only referenced in two of the executables, this DM client and download agent. So those are the ones that we're going to want to look at. So taking a step back, we look at where DM client and download agent get spawned. They get spawned within a process called OMA. Digging a little deeper, we see that this process handles OMA device management, which is the same protocol that your mobile phones use, that providers use to manage your mobile phones. So OMA DM operates on this DM tree structure, and DM servers basically can query fields in the tree, management objects in the tree. They can update management objects in the tree, write to them to basically update configuration and get status about the phone. And this vehicle, this telematics ECU, works the same way. So what you see on the left there is the DM tree for this specific ECU. You can see that was conveniently mounted in a file system partition that's mounted at /DM tree. And you can see the device, I can't read it from here, but device dev info and dev detail, those are standard OMA DM management objects, but then the firmware update object is one that's sort of specific to this. So based on this, we can see that this ECU is using OMA DM for firmware updates. I'm not going to show it, but if you dig down in there, download, there's a package URL that actually has a URL for an FTP server where this ECU goes out and actually tries to download the update for that, actually download the firmware update. If you're looking at OMA DM handling in the ECU, you see stuff like you would see on the right there in IDA Pro. So this guy is specifically handling, OMA DM requests to actually perform the download. So you can see him kind of checking the request, doing string compares on what came in, and then depending on what he sees, he processes the command. Either Flash Manager processes it or the Download Manager processes it. So back to our certificates. The first one we're going to look at is Download Agent, because why wouldn't we? Download Agent's a pretty interesting name. So Download Agent uses libcurl, which is an open source library. Libcurl is statically linked in. So previous talk, they talked about issues with third-party code usage. So it's not just third-party code libraries that you use, it's also third-party code that you statically link into your executables. Here, libcurl is statically linked in. So libcurl usage is pretty simple. You initialize the library, get a handle, set up a bunch of options, and then you use easy to perform, and libcurl goes off and it does the transfer for you. So looking at the options, we can look at the options for how the certificates are used. We see that vehicle cert is the actual vehicle certificate, vehicle PRI is the private key, and then root CRT is the root CA certificate. And using the other option that you see up there, we can see that this is an FTP request authenticated with SSL. So this whole download agent is basically going out and doing FTP requests to download the update package. The other process is DM client. You can see here's another case of third-party code. The Certicom SSL, if you Google Certicom, they actually do sell or do make an SSL package. So my guess is this is third-party code as well that was statically linked in. EMXP Connect, if you're like me and you have no idea what EMXP is, you would Google it. I actually found a patent for EMXP on the internet. So when you read the patent, it basically says that EMXP is a lightweight protocol that carries TCP IP over CDMA cellular networks. Makes sense. We already know that this ECU uses CDMA. And it was optimized for SOAP content to basically reduce some of the overhead that you see when transmitting SOAP over HTTP. The patent actually even has a very nice protocol stack, which you see over on the right. So we can see that, you know, our lightweight protocol's in the middle, then we have our MIME header and our SOAP, and the lightweight protocol header looks like that. So now that we know that we're using this EMXP thing, we can go back to our strings and we can do our string search again, and we see that download agent and DM client aren't the only processes that use EMXP. They're used in other things as well. We see a couple URLs that I've blacked out the IP addresses to protect the innocent, and a couple other things there as well. Okay, so what do we know? Just based on a little bit of reverse engineering, a little bit of hardware analysis, we know that this thing uses either CDMA 2000 or CDMA 1X. 3G would be CDMA 2000, 2G would be CDMA 1X to communicate with the call center. We know that OMA device management is used for firmware updates. We know that the primary protocol is EMXP over TCP IP, and there's a bunch of different processes that use it. We suspect that EMXP is used to transfer our OMA DM commands, but we haven't confirmed that yet. We know that at least the communications that deal with firmware updates are protected with TLS, and we have the client certificates for that. And we know that there's a hardware CAN controller integrated onto the main processor. So using all this, we can come up with an attack plan. So our first step would basically be to set up a rogue base station and try to push the telematics unit to CDMA 1X. A lot of telematics units and comms that support cellular, they support the 3G and 2G protocols in case they don't have access to LTE even to this day. And 2G protocols, both the CDMA and GSM only authenticate the network only authenticates the phone. The phone doesn't authenticate the network, which makes rogue base stations possible. There's well-known attacks on GSM, as in GSM uses weak encryption, and people have shown them to be able to break that. CDMA is a little better, but it also has some issues. They use some short keys, most notably the authentication key is 64-bit. So we might be able to push this telematics unit over to CDMA 1X and then man in the middle of the comms. So once we do that, we've got a couple options. We can attack baseband protocols, so we can fuzz the CDMA protocols. If we're successful there, we're probably going to end up on the QSC chip. And where we really want to be is we want to be on the NXP chip because that's where the CAN controller is. So we would probably have to do some additional work to basically figure out how to pivot from the QSC chip up to the NXP chip. So we could also then just go straight for the application layer protocols. We know that we're using EMXP, SOAP, and OMA DM. We also, if we got on the internet, we see that someone did a presentation, 2 researchers did a presentation on issues with OMA DM clients at Black Hat in 2014, so we know there's issues there. But doing this requires us to set up a server on our rogue base station to masquerade as the call center. If we're successful at doing that, I should say that we know that some of the comms are protected with TLS, but not all of them are, right? We only saw references to those certs in 2 processes. So we might be able to play some games there and then fuzz those protocols. We could also then just go after the firmware update process. So we could set up an FTP server on a rogue base station to try to masquerade as the actual FTP server, and then we could try to use OMA DM to convince our telematics unit to then try to download updates. Now this one's probably the most challenging because we know that all the update processes and the update messages are protected with TLS. So we'd have to kind of rely on errors in sort of the implementation there. Maybe they don't really validate the server certificate or something like that and would allow us to kind of set up a rogue server. So the one thing that I didn't mention, didn't have time to show, is that when we extracted the file system partition, what we get back is also the permissions for all the different files. So we see that the CAN handler and all the processes and all the files that handle the EMXP have the same file system permissions. So if we're able to get access, if we're able to exploit a vulnerability and get access to one of these processes that's doing the external comms, we might not have to do a lot of work to get access to the CAN handler. That's not true in all systems. A lot of systems have different permissions for like devices and things. So if you were to actually exploit a vulnerability and something handling external comms, you might have to do additional work to then basically find a privilege escalation that would allow you to send CAN or do something else. So that's basically where I'm going to stop. I think I'm over my time. Overtime? 1 minute? So does anybody have any questions in the next minute? Okay. Well, I'll be hanging out at the Booz Allen booth if you guys want to come up and chat about this or really anything else. Thanks very much for coming and listening. Thanks.